Okay, in this video, we're going to talk about chair conformations and how to draw them from a cyclohexane, as well as how to determine which ones are more stable. So the first thing that's kind of important to talk about is the two positions that substituents can be on a chair conformation. So on the left over here is the axial position, where you can see is when it's either straight up or straight down. So if the point on the chair conformation is pointing up and your substituent is also straight up and not at an angle, that would be an axial position. Or likewise, if it's also down and the point is down. And then on the other hand, equatorial positions are when the point is up, but your substituent is going down. And I'll explain how you figure that out in just a minute. But as you can see, these ones are angled and these ones are not. And I'll go over this again at the end, but just to clarify, in order to figure out which chair conformation is more stable, you want your bigger substituents to be in the equatorial position, so over here. And this just helps to avoid steric strain. Okay, so if we start with a cyclohexane like this, something that will help you draw your chair conformations is keeping your numbering the same every time. So you don't have to do this, but I think it's easier if you just start the one at the very top of the cyclohexane. That way you can kind of just keep it the same every time you do it. And then something else to keep in mind too is that when you have wedges, like this chlorine right here, those will be up in a chair conformation. And then when you have dashes, like this hydroxide over here, those will be down in a chair conformation. And I'll explain how you draw a chair based on this molecule here. Okay, so first you just want to draw out your outline. When you do your first chair conformation for numbering, I like to start numbering from one at the top right corner and just work your way around. Again, I think if you standardize this for yourself, it'll make it a lot easier. So the first thing we want to do then is put our chlorine at the one position over here in the one position. And you can see that the chlorine over here is a wedge. So that means it should be up. And if you're trying to figure out if it should be axial or equatorial, you come over to your chair conformation and you look over here at the one position. Since the point right here is pointing up and not down, and this molecule is supposed to be up because it's a wedge, your chlorine will look like this and it will be in the axial position. Um, on the other hand, if we move to the three position here to add our hydroxide, so this is a dash, which means that theoretically it should be pointing down, but our three position here is an upward point. So that is how you get an equatorial substituent on your chair conformation, which would look something like this. And then lastly, you can see our 4 over here, it's a wedge, so it should be pointing up, but the 4 over here is in the down position. So again, your methyl group right here will end up being equatorial as well. Okay, so as for the chair flip, you want to kind of draw everything so you can see your cyclohexane as well as your first chair molecule as you go, just because it'll make it easier on yourself. When you do a chair flip, I kind of draw a very similar structure. Some people kind of mirror their chair, but honestly, I found that you don't necessarily have to do that as long as you switch the numbering. So instead of starting your 1 at the top right over here, you're going to start from 1 at the bottom right, and then again, work your way around. And then something about chair flips is that your substituents will stay at the same numbered positions, but everything that's axial will become equatorial and everything that's equatorial will become axial. So we have the chlorine, again, it was axial here. When we do the chair flip, it's still in the one position, but in this case, it's equatorial. The hydroxide was equatorial in this case, but here it's going to become axial, again, still in the same 3 position. And then your methyl group, again, was equatorial, but it will be axial in the chair flip. Okay, and then lastly, if you're trying to figure out the stability of chair conformations, again, like I said earlier, you want your bigger substituents to be in the equatorial position to avoid strain. So if we look, these are actually chair flipped molecules of each other. So your biggest substituents are going to be these carbon groups that are circled here and here. But as you can see in the left molecule, these carbon groups are in the equatorial position because they're kind of at an angle. And then in the right molecule, they're in the axial position because they're straight up and down. So in this case, the left molecule is the most stable because your bigger groups are in the equatorial position.